Hello and welcome to Behind the Scenes, where we take a closer look and a deeper dive into our course material. Today I want to talk a little bit more about convolution. I want to try to give some proof or some justification, maybe not quite full-fledged proof, but something hopefully that ties it all together. So let's go ahead and let's start with some conditions. Let's say for t greater than or equal to 0, and tau greater than or equal to 0, we're going to have capital F of s be equal to the definite integral, the improper integral, from 0 to infinity of e to the minus s tau times f of tau d tau. And we're going to let or define capital G of s in a similar way. Here we're going to say this. I just want to use a different variable. Instead of tau, let me use variable u. So we'll say the integral from 0 to infinity of e to the minus su, I got any Syracuse fans out there, times little g of u du. Now to start moving into the territory that we want to be in with our convolution, we're going to make a substitution. Ooh, that kind of rhymed. Make that into a nice track for your mixtape. So let's go ahead and we'll say let's let u be equal to t minus tau. And if I differentiate both sides, here treating u as the variable on the left and t as the variable on the right, so differentiation with respect to u and with respect to t, I would get du equals dt. So that's nice. We also have to consider some change of bounds. So what we have starting with u is that u is in the interval from 0 to infinity, right? And so we'd say, well, what about when u is 0? Let's say when u is equal to 0, this means that 0 is equal to t minus tau. Or if I solve for t, I can just move tau over. That means t is equal to tau. And similarly, we would say, well, what about when u is infinity or unbounded, right? Well, that means that t would have to be positive infinity as well. So I can actually make this change and say that the function g, and it's still a function of s, right? The integration doesn't quite matter since I'm going to integrate and then I'm going to do an evaluation. So s is really going to be the variable that sticks around. But I can swap this out, make this variable replacement on u, and say that this is now going to be the definite integral from, instead of 0, my lower bound on t is going to be tau. The upper bound is still going to be 0. And we're going to have e to the power of minus s times, instead of u, we're replacing that, so I'm using parentheses, t minus tau. And then g of u is going to become g of t minus tau. And we said we can swap out du with dt. So now I get this in terms of t. And I have some mention of tau in there now with our variable replacement. Now from here, there's a couple of other steps I can take. So let me actually work through this a bit. So we'd say, okay, g of s, big G of s, the integral from tau to infinity of, now let me expand this out. That's going to be e to the minus st, and then minus s times minus tau is going to be plus s tau times g of t minus tau dt. And now I can use properties of exponential functions to break this up into the product of two exponential functions. I can say this is the integral from tau to infinity of e to the st, e to the minus st, times e to the s tau times g of t minus tau dt. And when considering this integral that we have, t is what we're integrating with respect to. So anything that has mention of t in it should be the subject of the integration, right? That's what the operator is going to act on. But I want you to notice that this e to the s tau term, it doesn't have a t in it, which means that we can regard it as a coefficient for the process of integration, so much so we can bring it outside of the integral. So we're integrating with respect to t, so any function of t, like this one here, and this e to the minus st as well, those have to stay to the right of the integration symbol. But this e to the s tau doesn't have any mention of t in it, so that can actually come out. So that's e to the s tau times the integral from tau to infinity of e, well, let me backtrack here. I don't want to write that one first necessarily. Does it matter? No, not for multiplying, but let me try to make this look as nice as possible. So we can bring the e to the s tau out, and we have the integral from tau to infinity of e to the minus st, g of t minus tau dt. And now there's one more claim that we want to make here, one more sort of mention, is I want to change this lower bound from tau to 0. And there's a bit of sort of motivation behind doing that. What we would say is we would say that we want, for working with our variables, we want to make sure that we're not doing anything that we shouldn't be doing. So a comment that we could make is we could say, in the interval where t is in the interval from 0 to tau, that our function g of t minus tau takes on the value 0. So we'd say in that case, if I get anything for t that is less than tau, then certainly I have everything to the right, From tau to infinity is the entire right-hand side of that interval. But if I have anything that's sort of more leftward, we would say, well, then our function g is just going to take on the value 0, which is going to produce the result 0 anyways. And we wouldn't typically want that because it's not going to give us anything useful, but we can certainly include it because it's not going to do anything. It's not going to affect our result. So finally coming to where we sort of want to be with this, we can make this claim that I've made above, that if t exists in the interval from 0 to tau, that the function g is going to take on the value 0, which is fine. It's not anything that we need, but in this case we want it. We would say that our function g of s, big G of s, can be thought of as e to the power of s tau, and then the integral from, I can fix this lower bound to 0, and say that anything from 0 to tau doesn't even affect the integral, so I'll include it anyways. 0 to infinity, of then e to the minus st, g of t minus tau, oh, don't move me, put me back, dt. Okay. So then I think we're just about ready to go where we want to go next with this. So now we would say, well, let's notice capital F of s times capital G of s. And I could go ahead and, for example, if I wanted to, I could introduce these pieces. I could also multiply them in the other direction. I could say G of s times capital F of s. And I can start introducing some of these things that I have. So we'd say, well, then this is going to be equal to G of s times, what do we say capital F of s was? Well, it was the integral from 0 to infinity of, and this was, we can go all the way back to the top. We first introduced this. This was e to the minus s tau, f of tau d tau. And since this function capital G of s is a function of variable s, I can treat it like a coefficient, I can leave it out in front, or I could do the opposite. I could push it into the integral. So I could go ahead and do that and say, well, let me bring it in then. Say this is the integral from 0 to infinity of e to the minus s tau times f of tau times g of s d tau. And now I can mention what we said g of s is. So we'd say, okay, well, let's keep going with this. We're all feeling good. I hope you're feeling good. I'm feeling great. We got the integral from 0 to infinity of e to the minus s tau times f of tau, and then times capital G of s, which we left this as, let me not be too hasty here, because we actually factored something out of it, or brought out a coefficient rather. We said g of s is this e to the s tau times the integral from 0 to infinity of e to the minus st g of t minus tau, right? That's what we had for this, dt. Then this was the integral times this, and this was d tau from original. So got this stuff here. I replaced my g of s. There it is. I'm multiplying by it, and then it was all with respect to tau for the outer integral. Now from here, things really start falling into place. So, make sure you're sitting down, buckle in, right? Because I want you to notice that since this e to the s tau is factored out, I could bring it out even further. It sort of already is out even further. I just want you to notice that e to the minus s tau times e to the s tau is going to give me e to the 0, which is 1. Right? Those just sort of eliminate each other in some sense. It gives me the factor 1. Which, okay, so then where are we going with this? Well, what are we left with? We have the integral from 0 to infinity, f of tau times the integral from 0 to infinity of e to the minus st times g of t minus tau dt, and then all of that d tau. But it just keeps getting better, because if I look at what's going on here, and I want you to focus on the inner integral, the inner integral is with respect to t. So this function of tau doesn't have any mention of t in it, and I can actually bring that into that integral. Think of it like a coefficient right now. I can bring it back inside, and I could say that this is the same as the integral from 0 to infinity of the integral from 0 to infinity of, and I can bring that f of tau in to the integral with respect to t, f of tau times e to the minus st times g of t minus tau, and that's an integral with respect to t, and then all of this d tau for the outer integral. Okay, well, so what about from here? Well, from here, something very nice that we can do is we can reverse the order of the integration. So we say instead of integrating dt and then d tau, since my bounds are the same, and there's some other justification as well that I'm not really going to spend time to show, but, follow me, trust me. We're all friends here. I'm not going to do anything to mess you up. We're just going to switch the order of the integration, which is perfectly fine in this case to do so. And if you're looking for justification on that, I can give you some ideas to where you can find some of that published. But let's go ahead and we'll switch the order of the integration. Since the bounds are the same, we're not going to notice that effect. We'd say the integral from 0 to infinity of the integral from 0 to infinity of, and I still have all of my stuff for my integrand, f of tau, e to the minus st, g of t minus tau. But now we're going to reverse the order of the integration, so it's going to be d tau for the inside integral, and then dt for the outer integral. This puts us in a really good place, because now that we've reversed the order of the integration, the inner integral is with respect to tau, so only the stuff that have a tau in it need to stay, which means that this e to the minus st term, which has no tau in it, can be treated as a coefficient, and I can bring it out in front. So just a lot of manipulation with our integral here. We'd say, now I can think of this as the integral from 0 to infinity of e to the minus st of the integral from 0 to infinity of f of tau times g of t minus tau, and that's d tau, and then all of this dt. Okay, so now we can make one final adjustment. Right, we can go ahead and talk about one last adjustment that we have to make here. Let's get the, what do we want? Let's go back to the purple. Get some more purple in here. So we started with some mention of variable u. If you remember all the way back, it's been a long time. But we said that u is in the interval from 0 to infinity. It doesn't really matter if that lower bound is included or not, since there's no sort of meaning to the integral at a singleton point. But something that we could go ahead and say is we could say, well, that means that u should be greater than or equal to 0, which means that since we made a substitution replacing u with t minus tau, that t minus tau should be greater than or equal to 0 to be in that interval from 0 to infinity. And this means if I add tau over, that t should be greater than or equal to tau. So t should be greater than or equal to tau. And what we can think about then is we'd say, well, okay, t should be greater than or equal to tau. In that case, I don't want tau to exceed t, or it's not something that should happen, right? If I go ahead and even rewrite the inequality slightly, we would say, okay, then tau should be less than or equal to t. So tau should not exceed t, and this integral with respect to tau is going from 0 to infinity. We'd say, well, it's not really that big of a deal, but it doesn't need to go to infinity. It shouldn't go to infinity. Variable tau should only go up so far as t. So if that makes some sense, then what we want to do is we actually want to swap out the upper bound there and say tau shouldn't have to go all the way from 0 to infinity. Tau should actually only go up so high as to t. And when I make that replacement, we get the integral from 0 to infinity of, we have this e to the minus st of the integral from 0 to, and not infinity, we're going to say from 0 to t, since bounds on tau only have to go up so far as t, and then of f of tau g of t minus tau, and that was d tau for the inner integral, and then dt. But if you take a look at what we have now, we actually have a special name for this inner integral. This is the convolution. Right? We'd say the integral from 0 to t of f of tau times g of t minus tau d tau is, by our definition, or by our nomenclature, however you want to think of it, this is the convolution f of t star g of t. This is the convolution of f and g. So we'd say, okay, that's very interesting to notice. So what am I actually working with here? Well, I have the integral from 0 to infinity of e to the minus st of f of t star g of t, the convolution, dt. But this should look very familiar as well. If I have a function, and try to think of this convolution of f and g as some function, and I'm multiplying that by e to the minus st, and then integrating from 0 to infinity with respect to t, this by definition is the Laplace transform of this convolution as the function. Right? We'd say, well, this is just some, it looks like it's just some function of t. So we're just talking about the Laplace transform of it. So this is equal to, here we have the Laplace transform of convolution, f of t star g of t. And this is where we wind up, but it's always important to remember our roots, who we are, how we are. Don't ever stray from your true self. Always follow your instincts, trust in your heart. The rest will guide you, of course. Where did this come from? Well, it's been a while, but this came from big F of s times big G of s. So now we can come full circle with this. So what do we have? We have big F of s times big G of s is equal to the Laplace transform of the convolution of little f and little g. That's little f at t star, little g at t. Or if you want to work with inverses, and we usually do, we would say that the convolution then, f of t, little f of t star little g of t is equal to Laplace inverse of capital F of s times capital G of s. And I am so happy to tell you that now we have some justification, some motivation, and some idea of a behind-the-scenes look of our convolution theorem. And here we have it right here. So let me know what you think about this stuff. Let me know if you found it interesting. A little bit of fancy footwork, especially working with the integrals and the bounds, and changing the order of integration. But otherwise, the result really starts to sort of piece together quite nicely. But I just wanted to give you some justification. Hey, whatever you're doing, I hope you're having a good time. Hope you're enjoying the content. I will see you